You hear me all right? So I have to say this is not fully a post-Bayesian talk, and maybe not even a fully Bayesian talk, but yeah, hopefully
everything.
Hopefully it'll be interesting. My goal is to kind of tell you how Bayesian inference and post-Bayesian inference can be potentially helpful in this setting of distribution robust optimization. And you're allowed to tell me that maybe it's not helpful at all. So open to feedback. This is joint work I did with Patrick Harita and Theo Domolas in the University of Warwick towards the end of my PhD. So the goal is to perform risk minimization. So we want to find decision Z that minimizes some risk, which is defined as expected cost under some data generating process B star, which is unknown. And this target doesn't have to be the data generating process. It can be any other target distribution. So this can also be helpful in the distribution shift settings. And of course, we don't know this target. For now, I'm going to assume it's the data generating process. And we have some finite data observations. And obviously, people will just then kind of find an estimator of p-n based on this data. So the kind of most common case would be empirical risk minimization, which is also what DRO generally is based on. But it can also be anything model-based. So you can just fit a model and use that. And distributional robustness generally looks at how much, basically, as a decision maker, you want to be affected on your decision if this estimator is far away from the truth. So as a concept, I think it's quite similar to, a lot of this post-Bayesian methodology, where you kind of start from this uncertainty, the data generating process. And how DRO proceeds is to say, if I want to be risk averse, I want to be protected, and I should minimize the worst case risk instead. So a worst case risk means I need to define some sort of set, which we call ambiguity set, around this, the information I have from my nominal distribution. And of course, there will be some parameter epsilon here dictating how risk averse I want to be, with very small epsilon, meaning I'm kind of back on the left-hand side. And there's a lot of ways people define this. One of the common ways is via some divergence or discrepancy. So there's a lot. There's just some examples where there's been all sorts of distance divergence studied in the optimization literature and the DRO literature generally. And how this works is, as you can see on the right, so imagine D is a metric, then you will have a Bayesian ambiguity set, which is centered on this nominal distribution. And then the general goal would be to choose epsilon large enough so that you include your target, but then not too large such that your decisions become overly conservative, because you don't want to include arbitrary distributions that are very unlikely to happen. And if you do include the data generating process, for example, or any target distribution, then you want that because you then upper bound your true risk, essentially. So what you're minimizing is as least as bad as your true risk. So if you're risk averse, this is something that you maybe want to do. So now I'm going to focus on model-based distribution robust optimization. So imagine we do have a model and we do have some posterior beliefs about our parameters. So assume we've done all the inference procedures. Then basically the question is, how can we use this information to define sets, ambiguity sets? And this can be either because I'm Bayesian and I've done this and I want to have some sort of worst case risk protection because I don't trust my data too much, or I don't have a lot of data, or maybe I think my prior kind of puts mass in all the wrong locations. But it could also be the other way around, where if I'm already in the DRO setting, can having Bayesian posterior beliefs help in any way to construct these ambiguity sets? And what we looked at, so the kind of first maybe natural thing to do is, if you look at let me go back, no. Yeah, okay. I'm lost now. Okay. Can I go back? No, no back. And that's it, I'm done. Okay. Oh yeah, thank you. Okay, so this is basically like a Bayesian risk optimization objective. So it's a bit like choosing the posterior predictive here as your nominal distribution. So nothing DRO-like. This is Bayesian risk optimization where you use the mean function as your risk function, basically. So if we follow kind of this this logic, like the first maybe natural thing to do is use the posterior predictive as a nominal. And then some divergence that kind of makes sense to consider in this scenario. Conceptually, this might not be people's favorite thing to do. I guess we already kind of had this from Sonia, that maybe the posterior predictive is not something that's supposed to be estimating the data generating process. But something different alternative you can do is actually define something that's kind of different shape than all the standard discrepancy ambiguity sets, which look at expected divergences instead. And that already, first of all, has potentially different shaped ambiguity sets, but also potentially eliminates this dependency on a single nominal. So you're already using all the uncertainty quantification from a posterior distribution to inform how this ambiguity set kind of looks like. And how you would want to choose the posterior and the discrepancy or divergence is based on basically what I've written here, maybe other arguments. But first of all, you need to be able to actually solve this optimization problem. It's obviously hard because it's on the space of probability measures or densities. You kind of want your ambiguity set to convert to something that's meaningful. So you want to, for example, at the limit of infinite data, to kind of at least go your ambiguity set to be around your data generating process or your target. And the properties of your posterior will probably also inform you on how you should choose the tolerance level. So how I saw you at the beginning that you want to upper bound your true risk, then normally people would want to use the posterior properties to say that that would hold, for example, with high probability. And finally, something we have to think if we are in the model-based case and not in the data-driven case is how sensitive this posterior will be to the model choice. So on the one hand, we want to use a model and posterior uncertainty to improve this ambiguity set, but of course, we're also inheriting all the sensitivity this might have. So first, and kind of first work we did with this, we just kind of saw what happens with a standard Bayesian ambiguity set, and we used the KL mainly because we were able to kind of show nice duality properties and actually solve this optimization problem efficiently. And also because it kind of gives you nice closed form solutions of what the worst case risk distribution looks like, and compared to other kind of Bayesian approaches to DRO, it gave kind of single state optimization problem that we still like a worst case problem. So I'm not going to go too much into other methods because no time, but there are other ways that people have tried to approach this problem, definitely. And maybe more of interest to this workshop, we kind of then started thinking that maybe this, I mean, it's nice when you have kind of a nice model, but it's probably very easy for things to go wrong. And this is because you're relying on this posterior quantification to define how conservative your decisions are going to be, essentially. And this is a quick example of how things can go wrong. So this is a typical kind of Hilbert contamination model case, but imagine you observe data from this contamination model, and your target is the clean part of the distribution. So this is just Gaussian distributions, kind of very simple toy example. And what we tried to do was kind of illustrate what the ambiguity sets look like. But of course, this is just approximate. So its point corresponds to a mean and standard deviation pair, so just one Gaussian. So we're only kind of looking at Gaussians. Of course, there might be other distributions in there technically. And this is also a very kind of common scenario in distribution shift settings, and you could also have it the opposite way. So you could also have a clean data set, but expect your test distribution to have outliers. And basically on the left, there is no contamination, and you can see the two ambiguity sets I showed to you, the smaller ones with a KL on the Bayesian posterior, and also a robust version where I'll talk to you about in a minute. And you can sort of see you're obviously losing a bit on the non-contaminated case, so you have a larger ambiguity set. But then when you add contamination, and this is based on exactly the same tolerance level, so I don't change anything apart from adding outliers to the data, then of course, the ambiguity sets are based on the Bayesian posterior get very much inflated. And they barely here include the data generating process itself. So of course, the worst case distribution here could be attained like somewhere here, and that could lead to very conservative decisions. So that's kind of a toy example to kind of say how maybe all these post-Bayesian posteriors could help. And yeah, so basically this is all to say that this kind of expected distances or using the predictive ambiguity sets can definitely be generalized to any sort of posterior that kind of fits the problem at hand. So, for example, a lot of these generalized Bayesian posteriors we've seen, and also, for example, this nonparametric learning posterior, which is still worked by Simon and Edwin and co-authors, and actually the special case of martingale posteriors. So they all kind of, not all of them, but a lot of them target some sort of distance. So this kind of loss function that replaces the likelihood function already uses a distance metric to target the parameter of interest. So the parameter of interest itself, it's kind of defined to be the parameter that's closest to the data generating process with respect to some distance. So what we thought was kind of interesting is to use the same metric of distance in the posterior and in the ambiguity set itself. And we used kind of this nonparametric learning posterior with the MMD. And yeah, and basically what we got is thankfully something tractable, although definitely a lot more computationally expensive. But in terms of conservativeness and out of sample risk, it definitely seemed to help in like simple situations where you just have a few outliers. So here, I don't know how much time I have, but okay, cool. So here you see out of sample variance and out of sample mean for this kind of very simple problem. It's called like Newsvendor or inventory problem, where basically you just want to decide how many units of products you should buy, and you pay some cost if you buy too many, and some cost if you buy too few. And here you see different values of epsilon, and from left to right, you also increase the level of contamination. And so in the well-specified case, as you would expect, this kind of standard Bayesian procedures definitely perform better in terms of trade-off of mean and variance. But then as you increase the contamination, they get really sensitive. So that's exactly what we saw about the inflated ambiguity set. And also, interestingly, the empirical version, which is just based on data and the MMD, still is more sensitive so as you increase the outliers. So even though we're in the model-based case, even just using data in this case, for example, that can be really sensitive to outliers itself. So here, basically, what are the takeaways? So one is that we can use Bayesian posterior beliefs if that's something that's available, and that's something that one wants to use to create this ambiguity set in the DRO setting. We definitely saw that properties of the posterior help inform the tolerance level selection. So I didn't really show that to you, but all the properties that we already have from all these post-Bayesian or semi-Bayesian posteriors are really helpful to prove results such as risk bounds, essentially. you do gain something by using a robust posterior, but there's definitely more to be done about making it more computationally friendly, basically. And the reason is mainly here due to the fact we use the MMD, and that creates an optimization problem in the reproducing kernel Hilbert space, which is quite expensive to solve. And yeah, I'm pretty sure if, this is still kind of preliminary work in terms of the MMD and the MPO posterior, but there's probably ways to still get a tractable optimization problem with other distances and posteriors that could also be more computationally feasible. So yeah, this paper's here if you're interested. That's it.
Thank you. We have some time for questions. All right. I can't remember if we spoke about it in the past, but was there something about taking sequences of those epsilon, those sets, either going to zero as you see more data, or like what that would mean for what we believe the contamination to look like in the acid?
Yeah, so the tolerance level, the way, I guess in both cases, is a function of how many data you have. And in the contamination case, also how much many outliers you believe to have. So that would definitely go to zero as you get infinite data, because as you get infinite data, your posteriors will target the parameter best describes the data generating process. So you expect your ambiguity set to just be a Dirac on the data generating process.
Even if the DGP lies outside of the...
Or, yeah, and of course, if model is misspecified, then you would get the model that best describes the data generating process in the sense of the distance you choose. So in the MMD case, it will be the MMD minimizer, for example.
Any other questions? Well, thank you very much for your question.
Thank you.